Today let us learn about division algorithm. The result is familiar to most of us when an integer a which is divided by a positive integer b in such a way that the remainder is smaller than b. We all know this. The exact statement of this fact is in the theorem which states given integers a and b with b greater than 0, then there exists unique integers q and r which satisfies a equal to qb plus r lies between 0 and b, 0 less than or equal to r less than b, where the integers q and r are respectively the quotients are called quotient and remainder in the division of a by b. In the division of a by b. This is the theorem on division algorithm. It says given an integers a and b with b greater than 0, then there exist unique integers q and r satisfying this property, where q is a quotient and r is the remainder. Before going to theoretical proof, let us look at few problems. Okay. Probably you might have come across with this type of divisions, say 44 divided by 6. Then you start writing like this and do long division method, and you find the quotient and the remainder. You write it like this, say 44 equal to quotient times the divisor plus the remainder. So this is my quotient and this is my remainder. Say one more problem, say 505 divided by, say something like okay, now you again go by this way and you write say 505 as 2 times the divisor plus 43. Yeah. Now this is my quotient and in this case this is my remainder. Suppose I have some negative number, something say minus 22 divided by 3. Okay. Now if you take only the positive part, then 7 3s are 21, you are getting the remainder 1. If you write it like this, minus 22 is equal to minus 7 into 3 plus 1, then this is wrong, right? You cannot just by taking positive number and doing long division method and attaching minus sign, negative sign to the quotient, it won't work. So you should write it like this, minus 22 minus 8 into 3 plus 2. Now in this case this is my quotient and this is the remainder. We all have done this method of division. This is called process of long division, which is nothing but the division algorithm. Now let us look at the theoretical point of this. Okay, so think of the number line now. So this is the number line. If I take minus 2b minus b 0 b like this, say 2b So somewhere here I have say QB and say Q plus 1B, Q plus 2B, like that. Okay. So when I take A can be equal to minus 2B minus B equal to 2B QB, like that. So there is two cases in fact. One case is A being a multiple of B. A is a multiple of B. When A becomes a multiple of B, either it may be minus 2B, B, 2B, like that. In that case, what happens? Remainder will become 0, that we have observed. Another case is if this A lies in between the multiples of B. A lies between the multiples of B. Means say somewhere in between this QB and Q plus 1B, in between this there is A. A is something somewhere here. In that case, the remainder is not equal to 0, right? And you can observe, say this distance is B and this distance is nothing but R, and this R is less than B, okay? And of course R is greater than 0, and in this case R is less than B. So that is what we have to prove. For the integers A and B with B greater than 0, there exist unique Q and R such that A equal to QB plus R, where R is greater than or equal to 0 and it must be less than B. So let us look at the proof. See, here I have to prove the existence of such Q and R which satisfies the equation A equal to QB plus R for with the boundary R greater than or equal to 0, less than B, and existence and the uniqueness of Q and R. Okay, so first we prove existence and then we'll prove the uniqueness of Q and R. Okay, let us take a set S. This is for the existence, okay, existence of Q and R. Sorry. So let S be the set of all integers of the form A minus xb such that x belongs to set of integers and A minus xb is greater than or equal to 0. Okay. To show this S is non-empty, say suppose A, if A is greater than or equal to 0, then what happens to this? For x being 0, A into 0b is equal to A. For the least, x is any integer, right? So when I take x is 0, A minus xb, A being positive, then this is equal to A. So which implies that this element belongs to set S. Okay. And what happens if A is less than 0? If A is less than 0, then say for any integer x, say it's a multiple of A, suppose, okay, say 2A, then A minus 2A into B, that will be A into 1 minus 2B, right? I know that B is greater than 0, it is given in the statement for any integer A and B with B greater than 0. So this is greater than 0. So what happens? Minus 2b, this whole thing 1 minus 2b will be negative, and of course A is negative, so negative into negative, that will be a positive integer, right? It will be a positive integer, and of course it belongs to set S. That is what I have taken. Set S is set of all integers in such a way that a minus xb is greater than or equal to 0, where x belongs to z. So my set S is non-empty. For any value of a, if a is greater than or equal to 0, then again element belongs to S, and if a is less than 0, then I can say elements belongs to set S. So I can say this S is non-empty by well-ordering principle. Okay, sorry, this set is non-empty, but now by well-ordering principle I can say that this S has a least element. Okay, right? So proved it is non-empty. So by well-ordering principle, set S has a least element. So let me call it as R. Say R. Okay. This means that R equal to A minus QB for some integer Q. And since R is in S, so this is in the form I have mentioned A minus XB. For some integer, R is nothing but A minus QB. Okay. Since I know that R belongs to set S and it is the least element in the set S, we have R greater than or equal to 0, right? Because S is set of all positive integers. So now we should show one thing is okay. For some integer Q, I have got the boundary for R, one boundary, lower boundary I have got. Now I have to show R greater than, R less than B. This I have to show, right? So we should show R less than B. For that, I will take a contradiction. I'll assume R is greater than B. Suppose what happens if R is greater than or equal to B. When R is greater than or equal to B, this is same as writing R minus B greater than or equal to 0, right? But we know that R equal to A minus QB, right? So R minus B will be A minus QB minus B. R minus B is A minus QB minus B. It is mentioned R minus B is greater than or equal to 0. So A minus QB minus B is greater than or equal to 0. This is same as writing A minus Q plus 1 into B is greater than or equal to 0. Right. But the thing is, R is greater than or equal to 0, right? See, R is greater than or equal to 0. What is R? R is A minus QB. This is greater than or equal to 0. Now it is saying even this is also greater than or equal to 0. But the thing is, I know this R, A minus QB, is the least element in my set S, which is the least positive integer in my set S. When I get Q plus 1B, of course this is less than this, right? See, this implies A minus Q plus 1 into B belongs to the set S, right? But thing is, this A minus Q plus 1 into B is less than A minus QB, right? A minus QB is what? A minus QB is nothing but R. So which is a contradiction to my fact that R is the least element in my set S, right? So This is a contradiction. Since R is the least element in set, yes, right. Therefore, R cannot be greater than or equal to B. R should be less than B. So now we found such Q and R which satisfies 0 less than or equal to R less than B such that A equal to QB plus R, right? So existence is over. We found such Q and R. Q and R with this condition. Okay. Now the thing is, I have to prove these two integers Q and R are unique. Okay. So for that, let me take two more integers. Say there exists Q dash and R dash in such a way that 0 less than R dash less than B and A is equal to Q dash B plus R dash. So to prove the uniqueness, suppose there exists another pair of integers say Q dash and R dash, okay, such a way that 0 less than or equal to R dash less than B and A equal to Q dash B plus R dash. Okay. Now I don't know whether R is greater than or equal to R dash or R is less than or equal to R dash. I have to prove the uniqueness of Q and R. It means that I have to prove Q equal to Q dash and R equal to R dash. So I'll take up with R. Say suppose I have to prove R equal to R dash and Q equal to Q dash. I have to prove this, right? So I don't know. I can take Q less than Q dash or Q greater than or equal to Q dash, and I have to prove, I can prove this is equal to this, okay? Or else I'll take R is less than R dash if I prove this, and if I can prove like this, then I can say that R equal to R dash, okay? So I'll take up one part, I'll just take up this, R is greater than or equal to R dash, and I'll end up showing Q equal to Q dash, therefore R equal to R dash, okay? So let me take, suppose R is greater than or equal to R dash. You can even take R less than R dash and prove, no problem. I'll take up the easy way. Suppose R is greater than or equal to R dash, then this is same as writing R minus R dash is greater than or equal to 0. Since I know that A is equal to QB plus R and equal to Q dash plus R dash, I can rearrange this statement like this: Q dash B minus QB is equal to R minus R dash. But R minus R dash is greater than or equal to 0. Therefore, this Q dash B minus QB is greater than or equal to 0. R minus R dash is greater than or equal to 0. Q dash B minus QB is greater than or equal to 0. Say, since B is greater than 0, it is mentioned for any integer A and B with B greater than 0, this Q dash B minus QB must be less than B. Okay, so that is same as writing that is same as writing 0 less than or equal to q dash minus q into b less than b. So if the whole equation is divided by b, then I'll get 0 less than or equal to q dash, it's no need of the bracket, q dash minus q less than 1. So q dash minus q is an integer which lies in between 0 and 1. It may be equal to 0 or it must lie in between this. But there is no such integer, therefore q dash minus q must be equal to 0. It must be an integer, right? Therefore q dash minus q must be equal to 0. What does it imply? It implies q dash equal to q. So one thing is over, then I have to prove this is what I have taken r greater than or equal to r dash, right? So if this q equal to q dash, then I have to check for the relation between r and r dash. I have assumed it as r greater than or equal to r dash, right? I just have to show r equal to r dash when q dash equal to q. Then see r equal to a minus qb, which is same as writing a minus q dash b, because q equal to q dash, which is nothing but r dash. Therefore r equal to r dash, right? Thus we found that there exists a unique pair of integers q and r such that 0 less than or equal to r less than b and a equal to qb plus r. So uniqueness is also proved. Hence we proved the existence and uniqueness of q and r, which satisfies 0 less than or equal to r less than b, a equal to qb plus r. This proof is quite tricky. You have to follow step by step so that you can remember the proof. So now let us look at the problems. The questions will be like, by using division algorithm, prove that cube of any integer is in this dash dash form, or square of integer is this form, like that. Okay, such problems will be asked. Let me take 2 or 3 problems. Okay, the first problem is, using the division algorithm, I have to prove that any integer is of the form cube of any integer is of the form 9k or 9k plus 1 or 9k plus 8. Okay, let a be an integer, any positive integer, and I'll take b equal to 3. Okay, b is greater than 0, you can take any values, but in this case for this you have to take b equal to 3. I'll tell you later why you cannot take any other value to b. Okay, first I'll take up b equal to 3 and I'll show you, then I'll come back to explain why I have to take b equal to 3. Okay, so if a is any positive integer and b is 3, then a equal to qb plus r, qb plus r, where q is greater than or equal to 0 and r less than b. Value of b is 3. So boundaries for so boundaries for r is 0, 1, 2. You cannot take 3, right? Because less than 3. So first case I'll take up by taking remainder equal to 0. So what happens when remainder is 0? A equal to 3 cube. Then I have to show cube of the integer. So this is my integer, I have to take cube. So a cube is 3q whole cube, which is nothing but 27q cube, which can be rewritten as 9 into 3 9 into 3 cube. This is same as writing 9 into k, where k is equal to 3q. So I got cube. If when the remainder becomes 0, then I got cube of this integer a is of the form 9k. Similarly, I have to prove for the remainder being 1 and 2. Second case where remainder is equal to 1, then a is 3q plus 1. So cube of the integer a is 3q plus 1 whole cube, a plus b whole cube, it's a cube plus 3a square b plus 3ab square plus 1, so that I can take up 9 common in these terms. So if I take 9 and q is also common, 9q, then it is 3q square plus 3q plus 1 plus 1, so that I can write this whole as k. Therefore 9q plus 1, 9k plus 1, where k equal to 3q square plus 3q plus 1. This is the case where remainder is equal to 1. So I got cube of an integer is of the form 9k plus 1. I have to check with all possible reminders. Okay, each reminder give you one form. When the remainder is 2, what happens when r equal to 2? In that case, a is nothing but 3q plus 2, so that a cube is 3q plus 2 whole cube, which is nothing but 27q cube. 27 into 2, 54q square plus 36q plus 8, which is nothing but, I can write 9q outside, so that it is 3q square 6q plus 4 plus 8, which is nothing but 9k plus 8, where k equal to q into 3q square plus 6q plus 4. I'm sorry, here I just missed one q. This whole thing is multiplied with this. I missed this q. Okay, here I have to write k equal to q into 3q square plus 6q plus 4. See, in this case, a cube of the integer is of the form 9k plus 8. Therefore, I can write a cube is either 9k, either of the form 9k or 9k plus 1 or 9k plus 8. Now the question is, how do I get the idea of choosing b is equal? Suppose if you choose b equal to 2 for any integer a and b is equal to 2, if you choose it like this, then a is 2q plus r, right? B can be any integer greater than 0, right? So if you choose b equal to 2, then a equal to 2q plus r, and the boundary for r is greater than or equal to 0, less than 2. Okay. Then what happens? Two possibilities for the values of r, either equal to 0 or 2. if r equal to 0, then a is 2q, right? A cube is 8q cube. Then this is same as writing something like this, 8k, where k equal to qq. Okay, now this is not in the form 9k or 9k plus 1 or 9k plus 8. In fact, you cannot write this in any one of these forms, right? So you cannot choose b equal to 2. You can even check with 4, 5, something like that. This form, getting this form from this is not possible. Therefore, we are taking b equal to 3. Okay.